In this two-part video on Red Hat OpenShift for Mass Platform Administrators, we will learn why Maximo got replatformed to use OpenShift and what are the key benefits gained from the replatforming efforts. I will go through the OpenShift components, the architecture, and how it works in the background. I will explain in detail on all the major components that makes the OCP platform. As a mass platform administrator, understanding these components and how all these are connected is critical to work efficiently. Part 2 of the video, we will focus on OCP mass architecture and operators and configures that gets deployed in the platform during mass installation. Understanding all these mass configs, related components will help the mass platform administrators to work efficiently and scale their skills. Before answering the question why Maximo got replatformed to OpenShift, those who have used Maximo 7.6 understand how it used to get deployed using IBM WAS and IBM WebSphere Application Server and the challenges that a monolithic application brings in terms of availability and scalability. So what is OpenShift? A simple definition I can tell that it's a container orchestration platform built on top of Kubernetes, which is again a container orchestration tool developed by Google. Its purpose is simple, which is to manage containerized application and its resources. So what Red Hat and OpenShift has done here is they took the Kubernetes and added layers of technologies to make it simple to install, configure, manage, and sustain with added security and compliance. Now we know that we are just dealing with an orchestration tool for containerized application. But what are the tasks or role of an orchestration tool? By end of this video, we will have all the answers clarified. So coming back to the slide, you can see 5 major points on why Maximo moved from WebSphere Application Server to run on OpenShift. And on the top of the list is monolithic to microservices. So monolithic applications are bundled applications. So code, config, UI, everything is bundled as a single unit and that application acts as a single piece of application. On the other hand, microservices are independent application components communicating each other to make up the whole service. So it's not, even though you call it one service, under the hood there are multiple services working together to make the whole service. In the case of, as an example, in the case of Maximo Application Suite, we have something called Mass Core. The Mass Core is a service, but there are multiple microservices running underneath the Mass Core to make up the whole Mass Core services. With microservices, we need containers. Containers are your application images. Either you use Docker to package everything and it's called image, or your container. With containers, we need orchestration. We bring the application as a packaged image and you put in a container. The container runs in the pod, which I'll talk in the next session. What are pods? But to manage all these containers and images, you need an orchestration platform. That is where the Kubernetes or OpenShift comes into picture. With the containerization of your application and the orchestration platform, the key advantage that we get is the high availability and zero downtime. The application can be available all the time and you don't have to take an outage or you don't have to take it down in case of patching or upgrade or anything. The platform can be managed without a downtime. And another key feature is the scalability. So you can scale the application easily without having to provision a lot of resources, right? We already have to size it properly. Within the size, you can scale up and scale down. And even you can scale your infrastructure faster than a monolithic application platform. Take an example, suppose you are getting 100 users requests to your app and you have 4 containers currently running to serve the 100 users. Now there is a seasonal demand coming up and you have to scale up your infrastructure to serve 1,000 customers. So you can, based on your application capacity and calculation, you can actually scale up all the containers. Maybe right now we have 4 containers. By a couple of button click or a couple of configuration changes, you can scale up the containers to serve 1,000 users. And scaling up is easy, that you are not rebuilding or reconfiguring it. It's simple as we are just telling the orchestration platform how many replica sets of your application is required. In following slide, we will learn what is a replica set, what is a configuration, what is pod. So the whole picture will be clear to you by the end of the session. So let's take a look at the foundational architecture for OpenShift. OpenShift cluster is built of worker nodes and master nodes. So you can see here in this diagram, I have 2 master nodes and 3 worker nodes. So the master node is sometimes referred as control plane nodes, and the worker node sometimes referred as the data plane nodes. So simple, it's easy to say master nodes and worker nodes. The master node is the brain of your cluster, where are some key services which manages and maintains the cluster. The orchestration framework is built. That is where the master node comes into picture. And we have the worker node, where is the compute, where your application containers are running. So generally you see X number of worker nodes, which means you depending upon the application requirement and the concurrent user load that comes into the cluster, you define the X number of worker nodes to satisfy that requirement or the service need. The master node is a lighter version of the worker node, because there are not any computational requirement there other than the general cluster OpenShift API services are running there. So you need to make sure your worker nodes are properly sized depending upon application need, but the master node is right size so that the Kubernetes or the OpenShift related components are properly executing in those nodes. Generally the worker nodes will have a process kubelets. The kubelets is a process or image that running on each of your worker node that helps the cluster communication. That means if worker nodes to communicate with the master node or with each other, these are the services that is going to help. Your application is going to run on each of these worker node. So if you remember the microservice oriented architecture, we will have multiple container images, and you can see the orchestration framework or the OpenShift here will schedule these pods or the containers in different nodes depending upon the resource availability. But there is a mechanism, each of these nodes can make API calls or internally communicate to provide you the services. Like the worker node, the master node also has some services running. One of the key services is the API service or API server. It's also a container image that's running in the master node. This is the service or server that actually giving you the communication inbound to the cluster. That means if you want to reach out the cluster, you need to have the service running. So in the diagram you can see that 3 services are connected to the API services or server, the UI, API and the CLI. UI is the OpenShift UI that you see when you log in, where you can manage the cluster. Behind the scene is actually invoking these services available in the API server. If you're performing in an automation or you want to customize a cluster using some kind of a script, of course you're going to hit the API server to get that service, that task completed. Similar, the OC commands or the CLI that is available will also depending upon the API manager or API server. The next critical service is control manager. It's responsible for managing the cluster. If you remember, the master nodes are the brain of your cluster, right? So the control manager is key service. As an example, if one of the pod needs to be restarted, the control manager takes on ownership to properly signal that restart to occur within the cluster. Another very important service is scheduler. Scheduler responsibility is to schedule the containers on different nodes based on the workload and available resources. So this is the service that actually look at the worker node, and if there is a pod needs to be scheduled, it determines which worker node is the right fit for the pod, and it is less use at that time. So that pod will be put into that worker node where it will start executing the application or whatever deployed to that pod. So it's a scheduler duty to actually look at all the worker node and understand the capacity where it can schedule ports. As an example, suppose you scale a application, that means you are actually scaling the port number of ports. Suppose if it's running in 2 ports right now, if you want to scale and serve more users, you want to double the number of ports, 4 ports. So the moment you tell the OpenShift to scale it up 2 more ports, OpenShift will request the scheduler to perform the scheduling of the port. So it's really important service. Another important service is the etcd database. It's a key value pair database which actually stores your cluster state. So whenever the cluster run, it keeps its configuration maps and everything, and that is stored in a key value pair. That is actually the state of the cluster. So at any point in time, if you want to restore a cluster, you can always fail back your etcd database to actually recover from that and go back to the previous good state from a failure state. So it is a critical database, key value pair, as I mentioned, which stores the cluster state information. As a administrator or mass administrator, you never deal with any of these services, but I'm just detailing it out so that you understand these are the main component that are available within the OpenShift architecture. Another key important component is the virtual network. It's a software defined network that is internal to OpenShift. OpenShift creates it. This is actually the way the worker nodes and master nodes and various ports are communicate to each other. It's a software defined network. You won't be dealing with these network components unless you want to do some core administration, next level of administration. But if you have to deal with some of the debugging where your pod is not able to communicate with each other or something getting blocked, yes, of course you need to understand how these software defined network or virtual network is working and what are the IP address assigned to nodes and ports. You need to understand those information to debug and resolve those issues. So as I mentioned, master node is critical. Worker node is not, right? So that means you can lose a worker node, still the cluster will work, right? If you lose all your master node, it's not good. The cluster is gone. You will lose access to the cluster. So ideally we need to have at least 2 master node so that we have a redundancy going on. So even one fails, the other one take over. So ideally we keep 3 master nodes in a production deployment, and the worker node is depending upon your production workload size. And always remember, you go bare minimum as a right fit for your cluster, but there is an option to scale up your worker node or add more worker node and provision more pods as we scale up. So that opportunity is available. Similarly, we can scale the master node also. We can add or remove master node, or you can even scale up master node as needed. So what you see in this slide is, as a mass administrator, you need to understand and manage whether you are installing or upgrading your cluster, or you are maintaining your cluster, or even you are looking ways to optimize your cluster or improve the performance. These are the major components that you will be dealing with in an OpenShift cluster. So in the left side you can see all the major components that I have listed out, and the right side is an example for me to explain each of these components and their role in your cluster. So here the first thing that you have to note is the node. Node is the server. It can be a physical or a virtual machine. That is the worker node, and you remember, based on your application requirement or the sizing, you will have multiple worker nodes deployed, and each worker node will have multiple container images running on it, right? So here in this example I am just showing one worker node, and I have the manage application and a MongoDB container images running on it. And you can see I have highlighted a red color boundary for that is the pod. So if you remember my previous discussion, the container image itself is not executable. You cannot just deploy container image. So any orchestration framework, what they do, they take the container image, create a abstraction layer on top of it, and the covered layer is called the pod. And every application usually deployed as pod. Ideally, one application per pod, but sometimes a pod can have more than one application, and or some of the helper functions or helper service container images can also be deployed along with the pod. So the best practice is to have one major application per pod and any associated helper pods if required. And you can see the app is our container image, whether it is Docker. You create a Docker image, you pull the Docker image from your registry, and when the scheduler tries to put into the worker node, they create a pod and it will go into the pod, and the pod is where it runs. Similarly, you can see here we have another pod running, which is the MongoDB community edition, or whichever we deployed. So we have two pods running in this worker node, which is a VM. And now let's take a look at how these pods communicate, because MongoDB needs to access the manage needs to access the MongoDB here, right? So whenever you deploy a pod into a worker node, by default OpenShift creates a virtual network. In the previous discussion we talked about the virtual network, the software defined network that the OpenShift creates, or any orchestration framework like Kubernetes, they create this virtual network. That is an internal network that is used to network all these pods and all these worker nodes to make a single bigger machine, right? So it connects all the worker nodes and all the pods, and all the pods and worker nodes communicate through this virtual network. So when you deploy a pod into a worker node, each pod gets an IP address. So here you can see that the manage pod got an IP address, and the MongoDB also got an IP address. So when you define or install, or when you configure OpenShift, the OpenShift asks for a CIDR block for internal network, right? It should never overlap with your public network. So from that CIDR block, it creates an IP address, and that is the IP address that is used here for each of the pod. So now this IP address is used to communicate between these pods. So the manage app uses this IP address to communicate with the MongoDB. But pods are ephemeral. Like that means a pod can die anytime. It can be recreated. It can be rescheduled. As an example, if this node do not have enough resource, the OpenShift cluster manager can evict this Mongo pod and provision in another worker node. Or if something happens to this Mongo pod, right, it can be recreated. So whenever a pod is recreated, it gets assigned a new IP address. So that's a problem. So because now the communication is broken, because it got a new IP address. So every time when a pod is created, whether it is MongoDB pod or here this manage pod, any pod is getting created, it will get a new IP address assigned, right? So that is obviously going to be a problem. That's why there is another component called services in OpenShift terms. So the service component is another static IP that we assign to a pod or a service, right? So what it does, the life cycle of pod is not dependent on the service cycle. So if you have an IP address assigned to a node or a pod, it will never change. As an example, so if you have a MongoDB service running here, it has its own IP, and I have created a service which I bind to this MongoDB service. Even a new pod is getting created and it's a new IP is assigned, but the service address will stay the same. It will be same IP. It will be going to be as an example, it will be the node IP address / the port of the application running. So it's never going to change, right? It is independent of the changes that are happening within the pod. So there are two types of service component: internal services and external services. So internal services are the binding that we do for internal communication. As an example, if your MongoDB wants to, if your managed application want to connect to Mongo, we can have an internal service defined. We don't want to expose the DB connection externally, so that's why we created the internal binding, service binding there. But from within the cluster, we should be able to use the IP address to get into the MongoDB. But sometimes you need to expose the services externally. That means you want to access the managed application via a browser. In that case, you define external services and bind that service to the corresponding port. The port binding and everything automatically happens. So usually the service IP address is the IP address of the node, and you use the IP address of the node, then the port these applications running use. So that means when a request comes to the service, it's always going to hit your node which is available in your cluster, and once it hit the node, it will look for the port that application running, and it will bind itself there. So that's why we are getting the response from the managed application in the browser. But if you bind a service, just a service, what happens? The URL won't be looking pretty, because there you will be using your HTTP slash the IP address of the node slash the application's colon the port name, right? To make it more convenient, suppose you want to use a app.domain.com, that is where the another component comes into picture, the ingress controller or ingress. This component is where you actually define your domain and how this routing actually happened to each of the services. So you create a ingress entry. As an example here, this case, if you remember the home to the mass application, right? So those are all ingress routes. So you create the ingress routes, and from that ingress route you bind the corresponding service, and from the service it will actually go hit the application. So all the customer or the client request actually hits the ingress from the load balancer, and from the load balancer from the ingress it goes to the service, and service is what giving you the response. So ingress and service is kind of an internal load balancer, because the service can load balance between multiple ports, and ingress also can do between multiple worker nodes, but you still need a actual external load balancer to load balance between multiple ingress controllers. So you'll be running ingress controllers in your worker node. That is where which understand how to route your request into which worker node and which specific ports that is running on each worker node. So you'll have a external load balancer, app load balancer, then you have the ingress controller, then you have the service underneath, and under the service needs you have the pod IP and the pod and the container image. So that's the whole hierarchy for your application.